Today we are very happy to have Xue-Yang telling us about the monopoles in QED3 and the Dirac spin liquids. And let's welcome Xue-Yang.
Thank you for the opportunity to talk at CMSA. My name is Xue-Yang. I'm a graduate student. And this work is in collaboration with Dr. Chong-Wang, Yin-Chen He, who are now faculty members at Parameter Institute, and my advisor, Ashwin Vishwanath at Harvard. There are two related papers that's listed on the slide. So the first paper is mainly, my first part of the talk mainly concerns the first paper, namely the consequence of this monopole point number. And the second part will consider the methodology of how to calculate the multiple point number. So this is a high-level summary of the indications of the work. So essentially, we are considering a 2+1 3-dimensional quantum electrodynamic QED, which flows to a conformally invariant fixed point, conjecture to flow to a conformally invariant fixed point. And we are concerning about the scaling operators in such CFT, such as the Fermionic bilinears, and more importantly, monopole operators. And this Dirac spin liquid is believed to provide a low-energy unifying theory for 2D quantum magnets, both on the bipartite lattice, such as square lattice, or non-bipartite lattice with geometric frustration, such as triangular lattices. On the technical side, the methodology used established a connection between the properties of a strongly interacting system, namely the monopole quantum number, with the fermion band topology, namely the linear center of a fermion spinon hopping model. And also, I'll briefly talk about recent progress in material experiments that reviews the promising candidates to realize Dirac spin liquid in the lab. I think for the audience here, we don't need much recapitulation on the 2D quantum magnets. It's like one of the central research area of condensed matter physics, and typically people concern the Hamiltonian with Heisenberg interaction plus some spin orbit coupling or like anisotropy term. What makes these 2D quantum magnets so interesting is the collaboration of this spin 1/2, which enhances quantum fluctuation, and also some possible geometric frustration. So bipartite lattice, we have the famous deconfined criticality, which unifies the Néel order and the valence bond solid order with deconfined critical point at the transition between these two ordered phase. While on non-bipartite lattice, there are many putative classical ground states for magnets. Say on triangular lattice, we have this 120-degree order states, and also these valence bond solid states with a enlarged unit cell containing 12 sites. And it's conjectured, it's found that this 120-degree order state has a Z2 mother state. The meaning we'll talk about in detail later.
So how robust is the deconfined criticality between Néel and VBS? I thought the bootstrap analysis rules out certain critical theories there with intense symmetry. So how robust is the argument from the other methods saying that you have a critical transition between these two phases?
I
Or is it just a
I'm also aware of like recent there are like numerical results that say this transition might be like first order.
That's right.
Right. So yeah, I guess that's a very valid point.
But it's not going to affect your talk.
Right. This doesn't really concern the talk of today. Yeah. But thanks for the comments. And a more exotic state on this 2+1D quantum magnet is so-called quantum spin liquid, where the spins didn't order even at the lowest temperature. However, they behave collectively. Namely, there are sometimes hidden long-range order, such as topological order, in the system. And it was first conceived by Anderson to be a precursor parent state for high TC superconductor, namely this resonating valence bound state, where spins with arbitrary distance between them form a spin singlet, and the ground state consists of superposition of all such arbitrary pairing of these spin singlet states.
For people who are not familiar with the concept, can you say again what's the parent state? What's the meaning of this term?
Right. So my understanding for parent state is that the cuprates upon doping will enter a superconducting state. At zero doping, it's conjecture that has an anti-ferromagnetic Hamiltonian in the spin sector, and Anderson conceived such an exotic ground state for cuprates at zero doping that upon doping might give a superconducting state.
I see. So it's some state for without doping, and once you consider doping, somehow it becomes superconducting state. So let's say it's a modification of the current state. Is that correct?
So that's the.
So is a superconducting state a modification of the current state?
I wouldn't say it's multiplication. It's
Modification.
like it's a, let's say, approximate phase for this current state. Yeah. Like if we change the parameters such as doping. And the exotic features for quantum spin liquids is emergent fermionic particles out of a bosonic system, and the so-called fractionalization phenomena. And there is also accompanying gauge fluctuations at low energy. So let's review the basics to study such exotic states. So we fractionalize this physical spin operator as a bilinear of fermion operators, this F, which is called spinons. By virtue of this anti-commutation relation, we see that such rewriting preserves all the algebraic relation of the physical spin operator. And moreover, this introduces a SU2 gauge redundancy. Namely, if we arrange the spinons in such way, then this physical spin operator stay invariant by a left multiplication of a SU2 matrix or a SU2 transformation of such spinor. And to proceed, the zeroth order is to decouple the spin-spin interaction, which is a quadratic fermion term, into a quadratic fermion term, namely performing this mean field analysis. And there is another important concept, which is called the invariant gauge group, called IgG, namely the subgroup of the SU2 gauge group that is preserved by this mean field ansatz. And for the specific case of Dirac spin liquid, we have a invariant gauge group of U1. Namely, the mean field ansatz we take is a diagonal form of this hopping matrix the spin up and spin down species are actually decoupled, and they each hopping with this Tij hopping amplitude. And to further characterize the Dirac spin liquid, we discuss such states on 4 lattices: square, honeycomb, triangular, and carbon. If we consider the hopping flux, namely the product of the hopping amplitude around certain plaquettes, and the square lattice is the so-called staggered flux state. You can see the neighboring plaquettes have hopping amplitude of phi and minus phi, alternating hopping flux. And we can also list some the hopping flux on triangular and carbon lattice. What's interesting is that although apparently, like at the surface level, the hopping flux breaks the translation symmetry, but actually by virtue of the gauge redundancy, we are able to restore the full translation symmetry and other lattice symmetry by compensating for a gauge rotation in the spinon sector. And at low energy, this is just a free spin-out model. There are 2 gapless Dirac cones for each spin species at half filling. Together, there are 4 Dirac fermions. And the low energy theory is described by this 3-dimensional quantum electrodynamics, namely 4 flavors of Dirac fermions coupled to the invariant gauge group U1, so coupled to a photon excitation. And there is a enlarged emergent symmetry at low energy, namely, besides this Lorentz group, there is also this SU4 flavor rotation that connects all the 4 Dirac fermions. And in addition, there is U1 flux conservation, namely the total flux of the U1 field is conserved if this ... doesn't include a monopole operator, which we will discuss later. So this state has been extensively discussed in previous literature as well, and by these people. And they find that this Dirac spin liquid actually has comparative mean field energetics in Kurzweiler projection calculation. And it's also interesting because the gaplessness is protected by all those lattice symmetries. Namely, all the possible fermion mass are forbidden by this by the symmetry of the system. And the as we
So the way to count this 4 is that true that there are 2 values of alpha and 2 values of S?
Yes, exactly, yeah. So for each spin species, there are 2 Dirac fermions, and they contain the so-called valid degree of freedom. And there are spin up and spin down 2 species, so 4 Dirac fermions in total.
So 4 Dirac fermions. I thought S is the speed label. So for given S, do you have still a 2-component spinner?
For single
Oh,
Yes,
S is
Flavor spin.
It's a difference.
SU2.
yeah, that's like the Lorentz spin. As we say, we are considering
Probably not Lorentz spin. No,
for
it's
each
flavor.
single
It's
Dirac
flavor
fermion.
spin. The S is the
Yeah,
flavor
so that's
spin.
additional
SO spin.
Lorentz spin in addition to alpha.
It's not written. Lorentz spin is not written.
Yes.
It's not written, right? Yeah. So for each side, it's also a 2-component spin. And we're concerning the scaling operators in this theory. So the first class of relevant scaling operators is the fermion bilinears. There are in total 16 fermion bilinears, and first one is a singlet mass, and the other 15 consists of either spin or valid degrees of freedom. And under this SU4 flavor rotation, they split into one singlet representation and the 15-dimensional adjoint representation. What's interesting is that these fermion bilinears have the same symmetry group as some microscopic order parameters. such as the Néel order and the BBS order parameters on square lattice. However, at low energy, they are all unified by this SU4 flavor rotation. So this already gives a non-trivial prediction that this algebraic spin liquid, as well, also called Dirac spin liquid, unifies the approximate ordered phase, namely the Néel order or the PBS order. And another class of scaling operator is so-called monopole operators. As we mentioned, the total flux of the small a gauge field is conserved. However, if the U1 gauge group is a compact gauge group, the gauge flux is defined modulo 2 pi, so it's perfectly legitimate to change the gauge flux during the path integral formulation by multiples of 2 pi. And monopoles describe such instanton events that is locally inserted and change the total flux by multiples of 2 pi. An elementary monopole change the flux by 2 pi exactly. And previous large n calculation, where n is the number of fermion flavors, here we have n equal to 4. This large n extrapolation shows that the monopole scaling dimension is near 1. So for 2 plus 1D theory, that's highly relevant. Namely, if a single elementary monopole is allowed by symmetry in the theory, this will drive the theory to confinement.
So what's n in large n?
Flavor.
N is the fermion flavor.
So large n means NF, large NF.
Yes. And second possible scenario is that instead of chiral symmetry breaking, say by intrinsic instability or by the tuning of some parameters, we generate a mass for the fermion to gap the matter field. And in this scenario, the low energy is a pure U1 theory. So this will always flow to confinement, namely monopole will always proliferate. And the resulting state actually depends crucially on the mass and the monopole that gets condensed. Namely, this symmetry breaking pattern dependent on the mass, on both the mass and the monopole symmetry quantum numbers. So I like to emphasize again that the chiral symmetry breaking mechanism consists of 2 steps in our work. First step is a spontaneous mass generation. And if it generates a singlet mass, then the singlet mass will have a Chen-Simons term that prevents the proliferation of monopole, and it will result in chiral spin liquid. If it generates one of the 15 adjoint masses, this will pick a certain elementary monopole and drive the system to some symmetry breaking states. And the detailed mechanism of how to pick a monopole will also be discussed later.
Excuse me, maybe naive question. Suppose the term that break chiral symmetry is singlet, is topological order, as you say. The last one.
Right.
Does that also have a choice for monopole? There's some additional subtlety for maybe which kind of topological order. I don't know, because you say the second case you need to choose monopole.
Yes, so the first case, because there is a Chen-Simons term for the U1, then it means like a magnetic flux is associated with a fermion. So this will suppress the proliferation of this monopole of magnetic flux. And this, I think this is the familiar chiral spin liquid that like breaks the time reversal symmetry and has the chiral modes, chiral edge mode. So as we mentioned, whether an elementary monopole is allowed and whether after symmetry breaking, what kind of state the system will enter. These all depends crucially on the symmetry quantum numbers of monopoles. To attack this topic, we use the state operator correspondence in CFT. Namely, a primary operator in a CFT inserted at the origin is mapped to a ground state in the radially quantized space. So here, a monopole operator is mapped to a ground state on a sphere with this 2 pi small a gauge flux threading out of this sphere S2. For the moment being, we ignore the gauge fluctuations. Under putting 4 Dirac fermions on a sphere under a 2 pi magnetic field will form a lambda level. In particular, each Dirac fermion will form 1 zero mode for 2 pi flux. And the ground state is obtained by filling all the negative energy states, namely the Dirac C. In addition, filling 2 out of the 4 zero modes, namely to the particle hole symmetric point. And in total, there are 6 different choices. So there are 6 degenerate elementary monopoles. 3 of them carries this spin 1 representation of the physical SO3 spin rotation group. For example, the shaded green area means that we feel 2 zero modes associated with both spin up. This carries a SC equal to 1 a spin density. That's one of the 3 spin triplet monopoles. And the remaining 3 are spin singlet, but they transform non-trivially under the valley SO3, so they are valley triplets.
Excuse me. Is the phi operator, the phi barrier you write there is also fermionic? You write phi Dirac C phi. Phi is also fermionic.
I think that's bosonic.
It's bosonic.
So monopole is the bosonic operator.
But you said Dirac C phi dagger. Just want to make sure what is it? You said Dirac C phi dagger.
Right. So yeah, I'm using this phi dagger to denote the Dirac C, namely the state with all the negative energy levels filled. And that's
phi is bosonic.
Yeah, that's bosonic system.
Well, it also depends on your definition of Fermat number. In the original paper, it was bosonic. The usual definition of Fermat number.
好多种风的 Dirac C， 就是从哪里看？
So I mean, each lambda level is fermionic mode.
Okay.
This has spin 0. Fair multiply spin 0. Space-time spin 0. That's a definite statement.
Right, and the zero mode carries 0 Lorentz spin as well.
Yes. So the here the SO3 spin again. That's the iso spin, right?
Yeah, that's the physical iso spin. Yeah, so the Dirac C carries also 0 Lorentz spin.
I mean, the monopole, of course, is always bosonic. It's a local operator. I guess the question is whether if you remove the zero mode filling, is it still bosonic? I guess that was the question. No. But they differ by filling 2 zero modes. Both are bosonic.
Yeah, so if we say there is a Chen-Simons term and the filling is not exactly at the particle symmetric point. Say we fill 3 zero modes out of this 4 zero mode, then it still carries 0 Lorentz spin, I guess.
That's more complicated. You're saying with the Chen-Simons term. I think the question was without the Chen-Simons term. then everything is bosonic. Both the physical monopole and the bare monopole, they differ by even number of fermion occupations.
Right, if they are all physical operators, and they should, like local operators, then it should be bosonic. The symmetry group we consider is the full space group of all the different lattices, namely the translation along two canonical directions and rotation, and also some internal symmetry such as spin rotation, which is fairly straightforward to fix, and time reversal reflection. I won't talk about this discrete time reversal and reflection. They require a bit more work. But if you're interested, we can discuss later, or you're welcome to read the papers. So we focus primarily on this space group quantum number in this talk. And to reformulate the problem is that how to embed all these microscopic symmetries into this enlarged low energy symmetry group, which, to be rigorous, is a SO6 flavor rotation, and this U1 flux conservation group, a direct product between them. So to fix the SO6 flavor rotation part is also quite straightforward. As we say, the monopole consists of filling all the Dirac C, which is a SO6 singlet, and two of the zero modes denoted by F. So each zero mode carries the same flavor rotation as the Dirac fermion from which it descends. And hence the monopole, the SO6 part of this monopole is fixed straightforwardly by its zero mode content. And what's tricky is the U1 flux part, because we know the Dirac fermions doesn't carry any charge in this symmetry group, and so it's only carried by the monopole and this so-called Barry phase of the monopole operator under symmetry transformations. Before we proceed, to know which fermion mass pick which monopole, there is a simple statement, because one fermion mass will split the degeneracy of the four zero modes, namely making a certain monopole energetically favorable. For example, if we generate a quantum spin Hall mass, say along the third direction, along the z direction, then the two fermion modes with spin up is lowered in energy. So the monopoles that fill in these two spin up zero modes is favored. Namely, in this case, the monopole that gets proliferated carries a spin z density. And straightforwardly for all the other masses, they are connected all by this SO6 adjoint representation. So we can also perform the same SO6 rotation on the monopoles to determine which monopole gets picked by which fermion mass. I should also emphasize that the 6 monopole forms a SO6 vector representation for the symmetry group. And I'll skip the methodology part, namely how to fix this U1 Barry phase, and we'll come straight forward to the bipartite, to the consequence. So on bipartite lattice, we find that there is always a trivial monopole. So this corresponds to the first scenario as we discussed the fate of QED3. Namely, a trivial monopole will always drive the system to confinement. And in this particular case, the final states, this trivial monopole breaks the full larger emergent group to a smaller group, namely SO5. And the theory with SO5 symmetry is still anomalous. So there must be some additional chiral symmetry breaking and drive this system to a symmetry breaking state. This
Sorry, please again how it breaks to SO5. So the singlet breaks to U1, but how do you break to SO5?
This, as we say, the 6 monopoles form a 6-dimensional vector graph of the SO6. Yeah.
This is not the singlet one.
Yeah, if there is a singlet one, namely the symmetry can be embedded into SO5, the remaining SO5. Yeah, so the rest of the slide is a bit technical. So for example, if we say the trivial monopole is V2, because it cannot carry spin indices, so it must be one of the value triplet monopoles. Say if it's V2, then there is a allowed coupling term between the fermion mass and the monopole operators. It looks formidable, but if we focus on these 2 shaded terms containing this V2, then it means that once the V2 monopole obtain a non-trivial, non-zero expectation value, then these 2 terms became more relevant compared to other like triple terms. So this means that the mass that's coupled to this V2 monopole is more likely to be generated during this chiral symmetry breaking. So namely, there are 5 masses, and what's notable is that these 5 masses correspond exactly to the microscopic order parameters of this Néel order and BBS order parameters. So this means that this system will flow and generate one of these preferred 5 masses, and will flow to either the Néel or the BBS order states. And more importantly, the condensation of this monopole operator doesn't further break any symmetry than the fermion mass already does, because they are coupled in such way, so they are symmetry equivalent in this case.
Sorry, how many type of MIJ there are?
15 MIJ. As we say, it contains both spin and valley indices, and excluding this one singlet mass, there are 15 left.
But here in this table, you discuss how many of them?
I discuss, I think, 5 of the preferred mass, and the spin Hall is three masses, so 8 of them. But we will consider the other remaining 10 masses. So if we tune the interaction by hand such that some other one of the other 10 masses is generated, and then there will be some unconventional orders other than the familiar Néel and BBS. For example, if a mixed mass, say both have both these spin indices and valley indices is generated, and a monopole that involves both the spin triplet and the valley triplet condenses. In this case, we draw schematically here the ordered state. It's a collinear spin order because the spin rotation along the I direction, where I is the spin indices for the mass generated, is still preserved. And it also breaks some lattice translation symmetry. And another feature of this state is that although it preserves a spin rotation, say along z direction, this state still has a non-trivial expectation value of this product of the spin Si cross Sj. So the spins, although they align anti-ferromagnetically, they still fluctuate in a quantum way, such that there is a non-zero cross product expectation value of the spins. And for the quantum spin Hall mass, we find that the quantum spin Hall mass will result in a state that fully breaks all the SO3 spin rotation symmetry. Because the spin rotation around the I direction preserved by the mass is further broken by the monopole that gets condensed. And the consequence for non-bipartite lattice, we take the triangular lattice for example, is that the monopole always carries a non-trivial U1 phase under these relevant symmetries. So this means that a single relevant monopole is forbidden in the theory. For triangular lattice, we find that the leading order relevant monopole operator is the triple monopole insertion. And this is likely to be irrelevant from the large N calculation. So it means that this Dirac spin liquid on triangular lattice is likely to be a stable spin liquid phase. And alternately, there might be other relevant operators in the low energy other than this monopole operator, namely this quadratic fermion term. This quadratic fermion term breaks the SU4 symmetry, but it preserves the subgroup of SO3 spin times ISO3 value. So it still preserves all the physical symmetries. And epsilon expansion or large N calculation gives different prediction on whether this quadratic term is relevant or not. So if it's relevant, then this Dirac spin liquid is a transition point, defined quantum point on triangular lattice between this 120-degree order and the square root 12 VBS states. And if not, it might be a stable spin liquid phase. And next, we'll focus on how the chirosymmetric breaking mechanism, namely generation of a mass plus the subsequent monopole proliferation, will produce all the classical order state on triangular lattice so far that has been found. So the symmetry breaking, the lambda order parameters of the symmetry breaking phase should have the same symmetry group as those of the mass and monopoles. That's the principle that guides our discussion. So for triangular lattice, we find that under translation, along either the Bravas lattice direction, the spin triplet monopole will acquire a phase of plus or minus 2 pi over 3. This is a very non-trivial result, as there is not a single fermion bilinear that has such momentum under translation. And to see the consequence of such 2 pi over 3 phase factor under translation, we first focus, say, on the case of a quantum spin Hall mass. And in this case, a monopole will get generated. Say along when I equals to 3, then the monopole S1 plus IS2 will get condensed. And as we say, we're trying to fix the symmetry group obeyed by these order parameters. So this monopole stays invariant under a translation T1 in combination with a spin rotation along the third direction by 2 pi over 3. Because we know that under translation, they acquire a phase factor of minus 2 pi over 3. So this phase factor must be compensated by an additional spin rotation. So this means that the symmetry group, the resulted ordered phase has to be invariant under a translation T1 and by a spin rotation of 2 pi over 3, which gives naturally the 120-degree orders. And a more non-trivial case is for the VBS order. So we know that this valley triplet monopoles has momentum by these 6 blue points marked in the Brillouin zone. And if we generate a valley triplet mass, then the valley triplet monopole will get condensed, and the resulting phase will have an enlarged unit cell because this new momentum of this valley triplet monopole will be the new Bravas lattice vector for the symmetry breaking phase. So we have a smaller Brillouin zone that has the area 1/12 of the original Brillouin zone, namely the unit cell is enlarged by 12 times. And similarly, there are also unconventional orders, such that if we generate some condensation of a mass that's mixed, that has both the spin and valid degree of freedom, this typically results in a spin, in a symmetry breaking state that both break the SO3 spin rotation and the lattice translation or rotation symmetries. However, they preserve one of the SO3 spin, a U1 subgroup of the SO3, namely the magnetic order is always collinear. And here are some schematic plot of these orders on triangular and carbon lattices. As we say, since this Dirac spin liquid really has a good chance to be realized in experiment, and here we plot the spectroscope, the signatures to look for in spectroscopic measurements, such as neutron scattering. And the first row is contains the momentum of the Fermionic bilinear, where the second row is the monopole quantum numbers. We see that there are some distinct features for the monopoles. For example, on triangular lattice, the monopole has momentum at k point, as we say, the 2π/3 phase and upon translation, and also these middle points between gamma and k. And on carbon lattice, the distinguishing feature for monopole is that the spin triplet monopole carries a non-trivial angular momentum 1 upon the C6 rotation. This predicts some smoking gun signatures to search for this Dirac spin liquid. Recently, there are promising progress on both the carbon lattice and the triangular lattice. So on carbon lattice, the group, a French group, finds that the archetypal system of Hilbert's mean-site has a sublinear temperature dependence of the relaxation rate in nuclear magnetic resonance measurements. And they extrapolate that the spin gap fitted from this data is extremely small. It's like 9 millikelvin. This kind of clarified the previous debate of whether the Hilbert's mean-site is a gapped spin liquid or not. So they claim that there is no spin gap in this kind of material, and it might be realizing this gapless Dirac spin liquid. And another material on the triangular lattice is the sodium ytterbium oxide. This material has very minimal chemical disorder, and aside from like linear temperature dependence of the heat capacity, they also find that upon applying a magnetic field, the system enters into a magnetic ordered phase, which means that the ground state, this disordered ground state, is driven by intrinsic this quantum spin fluctuation rather than some chemical disorder. And another group performed the neutron scattering measurements on this material and find a concentrated energy density at the wave vector, at the k wave vector, which is compatible with Dirac spin liquid prediction. So,
what's the figure? Figure B.
That's their putative phase diagram for the material.
What's the vertical axis? The magnetic field.
Magnetic field.
Why do you have a T?
Temperature dependence.
So you are drawing phase diagram T and the magnetic field, but magnetic field also depends on temperature.
Right, yeah. So this QD means quantum disorder. So they find that at low temperature, the spin didn't order. And I think this line is related
T
to
should be
spin susceptible.
Tesla.
Oh, Tesla. Sorry,
Okay.
T is the Tesla.
Yeah.
Sorry,
That's what you're saying. Yeah.
Okay, T is
So
the
the
Tesla.
unit, here is Tesla. In
Which
this
many
case,
Ts?
Kelvin. So to summarize, we find that this Dirac spin liquid might be a promising candidate for spin liquid states. And even if it's not stable, it helps organize the plethora of ordered phase, which kind of order parameter get enhanced in the vicinity of this Dirac spin liquid. And some feature of this chiral symmetry breaking order state is that a quantum spin Hall mass will result in a symmetry breaking phase that fully breaks the SO3 spin rotation, while a mixed mass will preserve one U1 rotation in the spin SO3 group. So it results in collinear magnetic order. While the Barry triplet mass will generate a valence bond order that preserve the SO3 spin but break the lattice symmetries. And there is a dichotomy between bipartite and non-bipartite lattice. Namely, for bipartite lattice, this QED3 actually flows to a ordered state. By fine-tuning, we can access this SO5 deconfined critical point. And on non-bipartite lattice, it might be a critical phase, and we can also predict, also back corroborate the approximate or symmetry breaking ordered phase by the quantum number of monopoles. So I'll briefly introduce the methodology of how to extract this Barry phase from monopoles. The difficulty actually arises from the fact that the Barry phase contains information of the microscopic, namely the UV physics in the system. For example, if we move the monopole, say rotation, we move the monopole in a scale of the lattice scale, and the Barry phase is accumulated during the process. So it depends sensitively on the microscopic details of the system. Jason Alicia has already attempted to calculate such a Barry phase in square lattice. And the first crude constraint is that since monopole operators are local operators, their symmetry quantum number should satisfy the algebraic relation faithfully of the SO6 of the low energy symmetry group. And by a stroke of luck, we are actually able to fix the translation Barry phase on carbon lattice purely from this algebraic relation. We find a spin triplet monopole. So under translation and rotation, they stay invariant up to such a Barry phase. And by playing with these algebraic relations, it's enough to constrain the Barry phase upon translation to be exactly zero. So we remark that here the rotation is very important for the discrete value of this translation Barry phase. And for triangular lattice, the translation Barry phase is fixed to one of the three alternatives, plus, minus, 2/3, or 0. It's also crucial to note that it's because the presence of rotation.
Just a naive question. So the monopoles also carry representations under the flavor symmetries. But
Yes.
But
yeah.
its Barry phase cannot be a non-linear.
Right. So
That's assumption.
because the flavor rotation part is very easy to fix, right? And we can pick a monopole, the spin triplet monopole, that stay invariant up to this Barry phase. So it means it's trivial. It has trivial elements in the SO6 flavor rotations.
Does it try?
By choice, yeah. So we only can. So for now, just pick one spin triplet monopole.
Okay.
Right. Yeah. And that stay invariant under this transformation. And all the other monopoles are related by this SO6 rotation, right? So once one monopole transformation, like
I was
transformation
asking something more naive. So I understand that different Berry phases for different components of the SO6 representation are related. But for a single monopole, why does the Berry phase have to be abelian?
It doesn't have to be abelian. As you say, like the symmetry group is non-abelian. It's just we can pick one spin triplet monopole that such that it because it's a valley singlet,
So
and all the
you're
like
picking
lattice translation all only transform in the valley SO3. So this spin triplet is a singlet under the valley transformation. So it's the invariant under the lattice symmetries.
I'm not sure you did.
I think
I still didn't
in other words,
get
she's picking a particular trivialization of this vector bundle generated by these monopoles.
why is that? It's always possible.
Well, he's making such a choice. She's making such a
This
choice.
particular choice of the monopole quantum number.
The trivialized SO3 part, but the non-trivial part is U1.
But the Berry phase here, well, you say non-abelian, it could not be just something like a rotation spin.
It could be the full SO6, right? SO6 times U1.
It should be quantum number equal, for example, maybe distinct monopole, in order to have non-abelian.
Yeah, maybe we can discuss it.
To do better, Yin-Chen performed a numerics to extract the monopole momentum. So namely, we put the 2D lattice on a torus and ignore the gauge fluctuation, just calculate filling the negative energy state and calculate the ground, get the ground state. And the monopole momentum is given by first translate the ground state and do a accompanying gauge transformation to restore the mean field Hamiltonian and calculate the overlap of the original ground state with the translated ground state. And we find that as we increase the system size, the amplitude of this overlap tends to unity. And the phase has been very well quantized to be 2 pi over 3 on triangular and pi on square lattice. So this gives this aligns also with the result of Alicia's result. So here the ground state also corresponds to a spin triplet monopole because, as we say, we want to exclude the tricky valley rotation part. There is also
Sorry, just make sure. In early part of your slides, you say that the gauge group is U1, so the series some QED, right?
Yes.
But I remember some slide you say start from QCD to QED. Do you say that?
Right, yeah, I didn't mention, but on square lattice or honeycomb lattice, there is always a trivial monopole, and there is a few theoretical proof. Namely, we can promote it to a QCD to prove that a trivial monopole must always exist. But that's a bit like irrelevant to today's discussion. But it's all in the paper. So in more analytical methods to extract the Berry phase concerning picking a particular monopole namely first getting out the spinon sector, for example, by a quantum spin Hall mass, and then we're picking a particular spin triplet monopole, the first step is to deform this spinon insulator to its atomic limit. So in this step, we make several assumptions. First, the gauge fluctuations are ignored. Namely, we are taking the limit of zero gauge coupling, and we assume that by this continuous deformation of the spinon band, provided we always respect the lattice symmetries of our interest during this deformation process. This process won't change the discrete symmetry quantum numbers of the monopoles. So namely, we can deduce the quantum numbers from this atomic limit in Dirac spin liquid. And the spinons, so as we say, rotation is kind of more elementary than translation in some way. And first we consider the rotation quantum number. As we know, the electric charge will move around a magnetic flux with C and AB phase. And conversely, when a magnetic flux moves around an electric charge, we also see the AB phase. So here, when the monopoles are rotated around some spinons located at the rotation centers, it will always pick up a AB phase that's determined by the number of spinons or like by the gauge charges located at the rotation center. The reason that all the spinons are located on rotation centers is because one has to preserve all the rotation symmetries. So all the atomic limit can be continuously formed to spinons located only on rotation centers. This principle contains a more important implication that for the spinon insulator, it's just a gap non-interacting system, and we are in an analytical, well-controlled limit. However, this limit actually gives us important knowledge about such a strongly interacting and gapless system by virtue of these assumptions. And a more elementary example for like how the binary center or the atomic limit of the spinons determine the monopole quantum number is for the slave boson formulation of the square lattice antiferromagnet. So in the Néel ordered phase, we rewrite the physical spin operator as a quadratic term of the bosonic fields. Upon translation, the bosonic field has to go through a particle-hole transformation as well because of the Néel-ordered formulation. A legitimate atomic limit for such bosonic spinons is one such that if we checkerboard color the square lattice, then all the spinons are located on one of the sublattice, say A sublattice. There is a spin up and spin down spinon located on each of the A sublattice. And this configuration preserves the lattice rotation and lattice transformation symmetry because of this special transformation equation. And we can see that once we subtract the background -1 gauge charge located on each side, then the monopole actually, when rotating around one lattice, it sees one gauge charge or -1 gauge charge. So namely, it carries a one angular momentum upon this C4 rotation. And that's in line with the symmetry of the valence bond solid order. So it means that once we gap the bosonic spinon and monopole proliferates, this new order will transform into a BBS order. So let's back to this Dirac spin liquid case. In our case, we have a free fermion hopping band problem. And to extract the atomic limit, we use the technique, namely to use the symmetry representation at high symmetry point in the Brillouin zone to extract the atomic limit that's been developed in recent years. For example, on the honeycomb lattice, the high symmetry point in the Brillouin zone is the gamma point and the M point. Here is denoted as 0 is the gamma point. Here is the representation of the spinon band in these two high symmetry points. One has to compare such representation with atomic insulator that preserve the rotation and translation symmetry on honeycomb lattice. And there are three types of such atomic insulator, namely the spinons located either on site or at the center of the edge or at the center of the hexagon. If we one should match the representation of such spinon band with the representation of these three kinds of atomic insulator, and we find that by this simple algebra, the atomic limit of such spinon insulator has one charge located on site and on edge centers, with -3 charge located at the center of the hexagon. And here, the -3 is related to the fragile topology, also discovered recently. It means that if we add 3 bands of this atomic insulator located at the center of the hexagon, together with the spinon insulator, then this system can be continuously deformed into the insulator with one spinon located on site and one spinon located on the edge center. And here, the monopole quantum number is actually also conversely gives a intrinsically interacting definition for this fragile topology. As we mentioned multiple times, for the triangular lattice, the remarkable feature of the translation benefits 2π/3 can be extracted directly from the atomic limit of triangular lattice. Namely, there is one negative charge located in downward triangle center and one positive charge located in upward triangle center. The translation is given by composing 2 rotations around downward and upward triangular center respectively, and by some simple algebra, we find that upon translation there is a 2π/3 phase. We remark here that this method established a mapping between the lambda order parameter of the symmetry breaking phase with the symmetry protected band topology of fermions, which in turn fixes the monopole quantum number and then determines the lambda order parameter of the symmetry breaking phase. Throughout the talk, I've been making various assumptions to justify the approach, and most of them are based on a large N limit. So first, in the large N limit, all the elementary monopoles carries a vector representation of the SO6 flavor group. And the second assumption is that when we deform the spinon insulator to atomic limit, we assume that the adjoint mass will flow continuously to infinity without encountering any singularity. So that's why the monopole, the kinematical property of the monopole will stay invariant upon this deformation. And the third one is to tune the gauge coupling and such that we could ignore gauge fluctuations. And there are also possible generalizations and implications for the work. So we can easily generalize it to Z2 spin liquid, where the Meson will transform projectively when rotated around a spinon. And in 3+1D, the monopole will transform, will carry a spin 1/2 representation of the SO3 physical rotation group, provided there is one spinon located at the rotation center. And a unresolved problem is whether it's possible to realize different barrier phase twice. As you remember that on triangular lattice, the translation barrier phase has three alternatives, right? It's either 0 or 2 pi plus minus 2 pi over 3. And here we find that they pick the 2 pi over 3 choice. But is it possible to realize, say, the 0 barrier phase or minus 2 pi over 3 on triangular lattice with the same PSG and with the same low energy theory? Or namely, to what extent is the monopole quantum network constrained by some anomaly? We partially resolve the issue and find that for the, say, the Z2 rotations, it suffices for the Lipschitz lattice constraint to give the quantum number for Z2 for Z2 groups.
So Z2 rotation.
For Z, yeah, for inversion. And another advertisement is that we have highlighted the importance of rotations that serve to discretize the monopole momenta. And in the absence of rotation, the monopole momenta is still a valid problem. And we find that it's related to the electric polarization. Here is the spinon polarization density in the system, and it's also discussed in a separate publication. This concludes the talk. Thank you.
Thank you. Very nice talk. Any more questions, comments? Do you expect something different from QCD3 systems? Some other richer phenomena?
Right, in QCD, we can also talk about different classes of instantons. That's definitely an interesting problem. I probably couldn't say much on that regard.
So for that case, is there some experimental system that realized those non-identity? Oh, you mentioned the SU2 case, right?
I think there is theoretical work on in 3+1D hierarchical or lattice that have SU2 gauge group in low energy numerical works. I don't know about any.
There's nothing like a non-PDS spin liquid in 2+1 dimension.
Usually it's not stable.
It's not, but this one is also not stable, right?
It can be stable. One can be stable. Like in triangular lattice.
In triangular lattice. But for the, you say for the non-abelian case, it's not stable.
Yeah, you need a lot of Fermi flavors. So usually we only can get a form. The form may not be enough.
Ah, right. Yeah, you need more. Yeah.
More, I guess.
Actually, this slave model, slave Fermionic construction, it seems usually people piece them on sides, and you will determine what kind of gauge field is there to start with. But for the story you discussed, can you do the same thing for the SU2 gauge field? Or is there some energetic constraint that you need to pick up one instead of SU2?
On square lattice and honeycomb lattice, the ansatz actually already have SU2 gauge gauge group. As SU2 as the invariant gauge group. Triangular and Coulomb lattice. There are definitely, we can definitely write down if you ansatz that preserve the full S SU2
Right.
gauge group. Right, but I think, yeah, as you say, it's constrained by energetics. So the Dirac spin liquid has been compared with other objects, say on company lattice, like the work by Xue-Yang, and they find that it has comparative infield energetics.
Okay. No more questions. Thanks, Xue-Yang, again. Thank you very much.